All right, so far we've looked at electrophilic aromatic substitution, but we can also do the opposite, nucleophilic aromatic substitution. So let's review again what we learned about electrophilic aromatic substitution. So here we have our benzene ring reacting with some kind of electrophile, and then it gets substituted in, right? So in this case, our benzene ring is acting as the nucleophile, and then we're adding an electrophile. But we can flip the script and do the opposite with nucleophilic aromatic substitution. So in this case, we have our benzene ring acting as the electrophile, and to it we add some kind of nucleophile. Overall, this is going to be a lot less common. Benzenes in general are pretty electron rich, so they tend to act as nucleophiles, not electrophiles. And so we need a number of things in order to make this reaction happen. The first thing that we need is we need a strong electron withdrawing group on our benzene ring. Most often, this is the nitro group. And the purpose of this is to make our benzene ring more electrophilic. Right, so you make your aromatic ring more electrophilic. The second thing we need is that we need a good leaving group. Most often, this is going to be some kind of halogen, usually either chlorine or bromine. Think about, SN1 and SN2 reactions. They both need good leaving groups. This also needs a good leaving group. And the last thing is that these two groups must be orthopara to one another. Right, so they have to be orthopara. They cannot be meta to one another. And if you think about the mechanism, it's easily explained why they need to be orthopara to one another. So let's go ahead and take a look at the mechanism. So here we've got a chlorine. And here we'll draw the nitro group as being in the para position. And then we have some kind of nucleophile. The nucleophile in this case is most often hydroxide. And so what hydroxide does is it's going to attack the carbon attached to your leaving group. We're going to then kick these pi bonds down onto our electron withdrawing group to form our intermediate. And then basically what's going to happen after this is that these electrons that just got bounced down to this nitro group are going to kind of bounce back up. So we're going to take this oxygen lone pair, make a double bond there, and then just bounce these electrons all out. And then in this case, instead of the hydroxide leaving, because it's a bad leaving group, what's going to leave is the chlorine because it's a good leaving group, right? So that's the necessity of the leaving group. We've got to kick something out of the system. And so what you can see here, what we've done is we've substituted out this chlorine for this alcohol. We can draw basically the same exact mechanism when the leaving group and the withdrawing group are ortho to one another, as opposed to para. All right, we can kick these electrons all throughout. Don't forget the positive charge on that nitrogen. I always do. And then we can simply take this and kick the chlorine back out. A little bit redundant with what we drew previously, but it's always good to draw these mechanisms multiple times to make sure that you understand them. If we try to do the same thing with the meta positioning of the leaving group and the nitro group, what you'll notice is no matter what you do, you can't get this pi bond to go up into the nitro group, right? It can only resonate around the ring, right? We can't get it up into here. And so that's why the meta doesn't work. So overall, the reaction mechanism is, or not the reaction mechanism, but the reaction scheme is you have some kind of usually a good leaving group like a chlorine or a bromine. You have some kind of very strong withdrawing group, usually a nitro group. What you do is then you add some strong nucleophile, usually sodium hydroxide. And then the second step here is to just add some acidic workup because you want to keep everything nice and protonated. Right, this proton comes from this acidic proton because once you make phenol, phenol is more acidic than sodium hydroxide, and so it'll be deprotonated. So go ahead and know that mechanism and know what you can do with that